Hello students, this is the third video of numerical solution series of chapter 1 of ICSE class 10 physics. Link of videos for solutions of numericals 1 to 12 are given in the description below. Numerical number 13. A physical balance has its arms of length 60 cm and 40 cm. What weight kept on the pen of longer arm will balance an object of weight 100 gram force kept on the other pen. So a physical balance has different arm lengths. So let us say this arm is having length 40 centimeter and here is 60 centimeter. What weight kept on the pen of longer arm will balance an object of weight 100 gram force kept on the other pen. So we want to find out that how much weight must be kept on the pen of the longer arm. Let us say this force is F2 and the weight kept in the pen of the shorter arm is 100 GF. Let us label this as F1. So we want to find out F2 such that this physical balance is balanced. So we can use the principle of moments according to the principle of moments. Anti-clockwise torque is equal to clockwise torque. F1 is equal to F2 d2. F1 is 100, d1 is 40, F2 we want to find out and d2 is 60. So F2 is 100 into 4 upon 6, that is 200 upon 3, 66.67 gram force. 14th, diagram in the figure shows a uniform meter rule weighing 100 gram force pivoted at its center O. Two weights 150 GF and 250 GF hang from the points A and B respectively of the meter rule such that OA is 40 cm and OB is 20 cm. Calculate the total anti-clockwise moment about O. Anti-clockwise moment here is generated by 150 GF. So we can say anti-clockwise torque is equal to force into distance, 150 into distance is 40. So this is 6000 gram force centimeter. This is the total anti-clockwise moment. Then we need to find out total clockwise moment about point O. Clockwise moment is here is generated by 250 GF. So clockwise torque is FD 250 into 20, that is 5000 gram force centimeter. Now third sub question is difference of anti-clockwise and clockwise moments. So the difference is difference in moments is 6000 minus 5000, that is 1000 gram force, and of course 6000 moment is anti-clockwise moment, so the resultant moment is also anti-clockwise. So we can say 1000 gram force anti-clockwise. And the last sub question is the distance from O where 100 gram force weight should be placed to balance the meter rule. Now see the difference in moment. In the previous question we found out 1000 gram force anti-clockwise. So naturally the additional 100 gram force now here must be suspended such that it must generate 1000 gram force clockwise moment. Okay. So 1000 gram force clockwise moment is due to 100 gram force weight placed at certain distance d from the center point O. So 1000 is equal to 100d, hence d is equal to 10 centimeter. So additional weight 100 GF must be placed at 10 centimeter on the right hand side of the fulcrum, that is somewhere here. We must place 100 GF. 15th numerical. A uniform meter rule of weight 10 GF is pivoted at its 0 meter mark. It's a uniform meter rule. So where must be the weight of the meter rule? Yes, you are right, 50 centimeter mark. And that weight is given 10 GF. Meter rule is pivoted at 0 centimeter mark. 0 mark. What moment of force depresses the rule? So here the moment due to 10 gram force is clockwise. So tau is equal to FD. Force is 10 gram force. Distance of that from the pivot is 50. So 500 gram force centimeter clockwise is the answer. How can it be made horizontal by applying a least force? See here, 10 gram force weight of meter rule generates clockwise moment. Okay, so now we must find out the least force which generates the same amount of torque but in anti-clockwise direction. So let us first find out the distance. At what distance it must be suspended. So we can say anti-clockwise torque is equal to 500 gram force centimeter. That is F into D is equal to 500. We want to find out the force, least force. Okay, least force. So for that, distance must be maximum. Distance must be maximum. So what is the maximum distance possible here? From 50 centimeter, maximum distance possible is 100 centimeter mark. So this force that we want to find out must be suspended at 100 centimeter mark or at 50 centimeter from the fulcrum. So we can say least force into 50 is equal to 500 and the force comes out 10 gram force. This is the least force needed. 16th, a uniform half meter rule. Now see here it is uniform but half meter rule. So the total length of the rule is 50 centimeter only, 50 centimeter. And it is uniform, that means mass must be concentrated at 25 centimeter mark. So this rule can be balanced at 29 centimeter mark. Okay, so weight is at 25 centimeter. It is pivoted at 29 centimeter mark. When a mass of 20 gram is hung from its one end. So weight of the rule here, half meter rule, will generate anti-clockwise torque, and to balance this rule, 20 gram must be suspended at 50 centimeter mark, right? Then only it will generate clockwise moment, and the meter rule, half meter rule, remains balanced or horizontal. So this is the diagram, required diagram, and to find out the mass of half meter rule, we can use principle of moments. So according to the principle of moments, anti-clockwise torque is equal to clockwise torque, that is W into 4 is equal to 20 into this distance is 21 centimeter, 21. So W is equal to 105 gram force. And since weight is 105 gram force, we can say mass is 105 gram. 17th, a uniform meter rule of mass 100 gram is balanced on a fulcrum at mark 40 centimeter by suspending an unknown mass m at 20 centimeter mark. So uniform meter rule, meaning mass is concentrated at 50 centimeter mark, weight of the meter rule is at 50, and it is balanced on a fulcrum at 40 centimeter mark. So fulcrum is on the left side of the weight, and it is balanced by suspending an unknown mass m at 20 centimeter mark. Okay, unknown weight is at 20 centimeter mark. Let's say that is F. Find the value of m. According to the principle of moments, anti-clockwise torque is equal to clockwise torque. F into distance of this force from the fulcrum is 20 centimeter. Right, this distance is 20 centimeter. Is equal to clockwise torque is due to weight of the meter rule into distance is 10 centimeter. This weight of meter rule is given 100 gram force. So F is equal to 50 gram force, or we can say mass is 50 gram. So 50 gram mass is needed to balance this meter rule. Second question here is, to which side the rule will tilt if mass m is moved to the mark 10 centimeter? See here, the mass m 50 gram is generating anti-clockwise moment, but it is balanced by the equal amount of clockwise moment generated by weight of the meter rule. Now if I shift that mass at 10 centimeter mark, anti-clockwise moment will increase. We can directly conclude that the meter rule will tilt in anti-clockwise direction. Anti-clockwise. What is the resultant moment now? Okay, so let us find out new anti-clockwise moment. Anti-clockwise torque is Fd, that is 50 gf into distance will now be 30, right? When we shift that to the 10 centimeter mark, its distance from fulcrum becomes 30. So 1500 gram force centimeter. So net moment will be sum of anti-clockwise and clockwise. Anti-clockwise will be 1500 plus, and clockwise is 1000 minus. So the net moment is 500 gram force centimeter anti-clockwise. Instead of writing anti-clockwise, we can say plus 500 gram force centimeter. How can it be balanced by another mass of 50 gram? Excuse me, this is not part of the question. So how can it be balanced by another mass of 50 gram? Another mass 50 gram must generate 500 gram force centimeter clockwise moment, clockwise torque. So 500 is equal to force is 50 into D. So D is equal to 10 centimeter. Alright, so additional mass 50 gram must be suspended at 10 centimeter mark from the fulcrum. And if you see from fulcrum 10 centimeter mark on the right hand side is nothing but 50 centimeter mark. So your answer can be D 10 centimeter or at 50 centimeter mark. 18th. In figure, a uniform bar of length L meter is supported at its ends and loaded by a weight W kgf at its middle. In equilibrium, find the reactions R1 and R2 at the ends. So see here we want to find out reactions when the bar is in equilibrium. It is very clear from the diagram that there is one downward force W kgf and two upward forces are there, R1 and R2. And when upward force is balanced by the downward force, then only the bar remains in equilibrium. So this is what we can conclude first, W is equal to R1 plus R2. Now to find out the reactions R1 and R2 here, we need to follow a particular procedure. First, let us consider that this bar is supported only on one support, only on one fulcrum. That is fulcrum number 1. Weight W is at distance L by 2 from the left side. And to balance this bar, a force is exerted at the end, at the extreme end, in upward direction, that is R2. Why this force R2 is in upward direction? Because see W, the weight will generate clockwise moment, so R2 must generate anti-clockwise moment to balance this bar. So we can say according to the principle of moments, anti-clockwise torque is equal to clockwise torque. Anti-clockwise torque is due to R2, its distance from the fulcrum is L, clockwise torque is due to W, and its distance from the fulcrum is L by 2. So R2 becomes W by 2. Once we get R2 as W by 2 kgf, we can use the first relation, W is equal to R1 plus R2 to find out R1. So we say W is equal to R1 plus R2 is W by 2. So R1 also becomes W by 2 kgf. Instead of taking fulcrum at the left end, you could also take the fulcrum at the right end and consider R1 as a required force to balance this bar. Okay, so again, by using this particular method also, you will find out that R1 is equal to W by 2 kgf. And then once again, you can use this first relation to find out R2, which would ultimately come out to be W by 2 kgf. Thank you. Please like, share and subscribe to my channel.